Hello everyone, it is good to present the solution of AP Chemistry 2021 free response problems, problem number 2. Now let's think about the atom, atomic structure, and the compound. Answer the following questions about the element silicon and some of its compounds. Problem A, the mass spectrum of a pure sample of silicon is shown below. Let's see. Interpretation of a graph is a critical component of a scientist and people who especially studying in the field of science and engineering. Let's think about it. First, what we need to do in this Cartesian coordinate is to see what is on the x-axis and what is on the y-axis. Let's look at what is on the x-axis. The x-axis title shows that it is mass and the unit is atomic mass unit AMU. 27, 28, 29, 30, 31, and 32. Relative abundance is on the y-axis, from 0 to 20, 40, 60, 80, and 100%. And out of these different mass, we have 28, 29, 30 shows some data, some bar graph. And out of that, 28 has the highest peak, and is in between 80 and 100%. Here, what I need to draw your attention is to see the difference between mass and mass number. What is mass and mass number? Mass is actually measured in this spectrometer, mass spectrometer, and it is always has fractions, has at least 2 decimal places, 3, 4, 5 decimal places. And mass is a fraction, but mass number is defined as the number of protons plus number of neutrons. So it is always an integer, always a natural number, always an integer, either 1, 2, 3, 4, 5, so on and so forth. Let's see the example. Carbon is most important atom in the periodic table, especially in relation to the human life. In my body is composed of basically carbon and hydrogen, and some of the oxygen, some of the nitrogens. And carbon, most abundant isotope of carbon is carbon 12, but we have carbon 14 too. Let's look at carbon 14. The symbol to represent this isotope is carbon 14. So here, let me correct. This is not copper. I wrote copper, but this one I need to correct. This is carbon. Carbon 14. 14 is representing the mass number of protons and number of neutrons. The mass is 14.003 AMU. As you see here, mass number is integer, mass has at least some decimal places. But they are very similar, as you see here. So mass is approximately equal to the mass number. So what is shown in this graph is mass, but we can approximate it into a mass number. Number 1, how many protons and how many neutrons are in the nucleus of the atom of the most abundant isotope of silicon? Isotope. What is the meaning of isotope? Here, we need to understand the prefix iso. Iso appears frequently in chemistry. Iso means in Greek word, same but different. So in some aspect it is the same, but in other aspect it is different. Here isotope meaning the atoms with the same number of protons, but different number of neutrons. And an atom of the most abundant isotope of silicon is the bar graph. When you look at the relative abundance of the bar graph, the highest peak, that is the most abundant isotope of silicon. In this case, we find the mass is 28, which is approximately to mass number 28. So the symbol is silicon 28. Now let's go to the periodic table. Let's find the location of silicon. We have hydrogen, helium, lithium, beryllium, so on and so forth. Silicon is found in period 3 and group number 4A. And when you look at the silicon has 14 and 28.09. The symbol of silicon is in between At the top, we have a number 14. At the bottom, we have 28.09. What does it mean? The 14 is atomic number. Atomic number is equal to number of protons. Proton is invariable in a chemical change. So we are using number of protons as a reference number to identify an element. Now the 20.09 is mass. Mass is averaged mass of all the isotope. So we have here silicon 28, 29, 30, three isotopes in the silicon. When you consider its relative abundance and get the average mass, then it is 20.09 AMU. So now we can have now answer from this periodic table. We know silicon has 14 protons and silicon 28 is the most abundant isotope. So the mass number 28 is equal to the number of protons plus number of neutrons. Number of protons is 14, number of neutrons is unknown. Let's plug in into the equation. 28 is equal to 14 plus number of neutrons. So when you rearrange it, when you subtract 14 from both sides, we calculate n is equal to 28.28 minus 14, which is 14. In this case, silicon 28, number of protons and number of neutrons are equal. Many times this is the case. So for the atoms with the atomic number 20, which is calcium, up to calcium from hydrogen up to calcium, many times the most abundant isotope is number of protons is equal to number of neutrons. Now let's move on to number 2, write the ground state electron configuration of silicon. Then let's use the periodic table as our guideline to write the electron configuration. So this one is showing the partial part of the periodic table from hydrogen to argon, and hydrogen, helium, lithium, beryllium, boron, carbon, so on and so forth is written. And the column is group number. Here is 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A. When I write this one in A, not just saying 1, 2, 3, 4, 5, 6, then it is representing that these elements are main group elements, not including the transition group elements. And the row, top row, second and third, we call this in period. Period 1, period 2, period 3. So silicon belongs to period 3 and group 4A. Now let's look at its electron configuration. So the closest noble gas is neon. So silicon has a neon core and 3s. Here is period 3. So this one, the first two column is S block. The right hand side 6th column belongs to P block. So sodium has 3s1 and magnesium has 3s2. Aluminum has 3s2 and 3p1. Silicon is adding one more electron in 3p subshell, 3s2, 3p2. So when you write all the neon, the core, and it is 1s2, 2s2, 2p6, neon has 10 protons and 10 electrons. And in this configuration, electron configuration, we see that 1s2, 2s2, 2p6, this one is called a core electrons, and 3s2 and 3p2. When the principal quantum number is the highest, the 3 is a principal quantum number, we call this one valence shell. In that valence shell, we have 4 electrons. In 3s subshell 2, 3p subshell 2, total 2 plus 2, 4 valence electrons. Number of valence electrons is very important. And all the elements in group 4A, carbon and silicon, germanium, so on and so forth, they have 4 valence electrons. That's why their properties are similar. Let me write the electron diagram to represent and understand the state of electrons better. This one is neon core, and let me write the orbital with the line. And in 3s subshell, we have 2 electrons. Their spin must be the opposite. In 3p subshell, we have 3 orbitals, 3px, py, pz orbital. Their shape is exactly the same. The energy level is the same. We call this one degenerate orbitals, but their only orientation is different. So when you fill it up electron in 3p subshell, we are filling up singly first with up spin. So up, we're filling up. So that's the electron configuration and diagram of the silicon. Now let's move on to the next problem. Two compounds that contain silicon are silicon oxide, silicon dioxide, and silicon tetrahydride. At 161 Kelvin of temperature, silicon tetrahydride boils, but silicon dioxide remains as a solid. Using principles of interparticle forces, explain the difference in boiling points. So it is helpful to write the Lewis diagram. In order to do that, we need to count the number of valence electrons in each element, in each atom in the structure. Silicon belongs to group 4A, just below carbon. So it has 4 electrons, 4 valence electrons. So let's write the single dot around 4 sides, and hydrogen has only 1 valence electron. Oxygen belongs to group 6A. It has 6 valence electrons. So it has 2 lone pairs and 2 unpaired electrons in its ground state. Let's draw silicon dioxide. It is called silica. Silica is forming a network, and silicon and oxygen forming so much of networking connected together like graphite. Graphite is pure carbon, but carbon is all connected to each other with covalent bonding, forming a network. Or, excuse me, or you can write the silicon dioxide as a molecular form. Sometimes silicon dioxide forms a molecular form. It is silicon and oxygen double bonding when you consider the octet requirement of silicon and oxygen. And so network of silicon oxygen is very stable. That's why at low temperature, they are all contained, forming a solid, and its melting point is very high. Melting point is over 1000 Celsius, very high because of this networking structure. What about silicon tetrahydride? Silicon tetrahydride has different structure. Silicon at the central position and hydrogen at the corner of this tetrahedral shape. And let's think about the electronegativity and electronegativity difference between silicon and hydrogen, each covalent bonding. Electronegativity difference value is 1.8 for silicon. Silicon is a metalloid. So electronegative value is less than the electronegativity values of the nonmetals. Hydrogen has the smallest electronegative value among the nonmetals, but still higher than the electronegativity of silicon. So then let's calculate the difference, 2.1 of hydrogen minus 1.8, which is 0.3. Our criteria for nonpolar covalent bond is 0.4. When the electronegativity difference is in between 0 and 0.4, the bond is covalent and nonpolar covalent bonding. Here, silicon and hydrogen, all of the bonding is nonpolar covalent. So there is no dipole moment in the bonding. So when you add up all the nonpolar covalent, the molecule becomes nonpolar molecule. So it is a nonpolar molecule. The intermolecular force, we need to think about intermolecular forces. Let's remind ourselves about different intermolecular forces. We have dispersion force, sometimes called London dispersion force. This is a default force present in all molecules. And we have dipole-dipole moment. We have a dipole-dipole force and hydrogen bonding. Dipole-dipole force and hydrogen bonding, the relative magnitude of intermolecular force is increasing. And dispersion force is relatively weak intermolecular force. Because this one has a molecule, forms a molecule, and the dispersion force is only this intermolecular force, it is boiling at a low temperature. So as we heat it up, this compound, it is the temperature at 161 Kelvin is good enough to overcome the intermolecular force of the liquid and making it into vaporizing. Now let's look at next problem. At high temperatures, silicon tetrahydride decomposes to form silicon, solid silicon, and hydrogen gases. Here, I want to draw your attention to the hydrogen gas. Hydrogen gas, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, the 4 halogens, they are all diatomic molecules in this standard condition, meaning 1 atm and 25 degrees C of temperature. So when it says hydrogen gas, we need to remind ourselves that we need to write it. The formula is H2, not just hydrogen. So when I teach the chemistry to the students, sometimes students make a mistake. Hydrogen gas is monatomic. No, it's not monatomic. Monatomic hydrogen is very reactive, and stable hydrogen gas is diatomic molecule. Okay, once you know this one, we can write a skeletal formula. Silicon tetrahydride is going into the reactant and decomposes to form silicon as solid and hydrogen gas in gas phase. Let's specify its state as solid and gas, writing out S and G. Now, number of atoms are conserved in this chemical reaction. Only their arrangement, chemical bonding is dissociated to form new chemical bonding. So when you match the number of silicon atoms and hydrogen atoms on the left-hand side, right-hand side to balance the equation, we find that the coefficients of hydrogen must be 2. So it is 1 to 1 to 2 ratio. A table of absolute entropies of some substances given below. Hydrogen and silicon tetrahydride is absolute entropies given 131, 18, and 205. Problem D, explain why the absolute molar entropy of silicon is less than that of hydrogen. Let's focus on its state. Silicon is a solid state. Solid state meaning silicon is forming a networking with another silicon, and it is, because it is solid, there is a very restriction of its movement. Silicon atoms are fixed and locked up in the position. Only vibration is allowed. Silicon is a little bit vibrating, little bit dancing. Sheepishly, it cannot move, it cannot rotate. Only the rotation, only small amount of vibration is allowed for silicon. So the freedom of motion is very limited. What about hydrogen gas? In gas formula, in gas state, hydrogen gas, between the particles, the distance is relatively large. So hydrogen gas is relatively freely moving and taking all different motions, freely rotating, vibrating, and moving from one position to the other. So in this state, hydrogen can take many different states. We call this one microstate. Is more higher number of microstates are allowed for hydrogen. So hydrogen has higher entropy. Generally speaking, gas state has higher entropy than liquid state, and liquid state has higher entropy than solid state. Now let's look at this balanced equation again and calculate the value of reaction entropy for the reaction. So absolute entropy given 25, 205, 131, and 18. And remember that all the functions of these thermodynamic functions, starting from internal energy, enthalpy, and entropy and Gibbs free energy, they're all a state function. The reaction enthalpy, entropy, Gibbs free energy is independent of the pathway from the reactant to the product. Only the value of the product and reactant matters. So we can, for a state function, we can calculate the value like this way. Reaction entropy can be calculated, the product absolute entropy multiplied by its coefficient, and we have to do the same thing and subtract product minus reactant side, where n is the coefficient because the absolute entropy is given per mole. So let's do that. Product side, we have 2 moles of, the coefficient of hydrogen is 2, so twice of 131 plus 18 minus 205, which is 75 joules per mole K. All right, so the entropy change of the system of the chemical reaction that we are interested in is 75 joules per mole K. Now let's move on to understand the spontaneity of the chemical reaction and reaction rate. F, the reaction is spontaneous. The reaction is thermodynamically favorable. In other words, this reaction is spontaneous at all temperatures. Low temperature, high temperature, doesn't matter. At all temperatures, the reaction is spontaneous and thermodynamically favorable. Explain why the reaction occurs only at high temperatures. So this one is some discrepancy. We expect the reaction occurs spontaneously at all temperatures, but In actuality, the reaction only occurs at high temperatures. Now, let me explain to you what does it mean. This thermodynamically favorable, the reaction occurs only at high temperatures. Here we are looking at two terms. First, thermodynamically, and second is kinetically. In order to understand thermodynamic terminology, let's look at the reaction enthalpy. First, let's think about formation enthalpy. Silicon tetrahydride, hydrogen, and silicon. I found out this formation enthalpy from the back of the textbook. Formation enthalpy silicon tetrahydride is 34.3 kilojoules per mole, but hydrogen and silicon is 0. Why? Remember, formation enthalpy is defined as forming the compound or chemical species from its most stable element. Most stable element of hydrogen and silicon is itself. For example, hydrogen, from most stable element hydrogen gas to hydrogen gas, it is a nil reaction. There is no reaction. So then formation enthalpy for the element, all the element is 0. Stable element is 0. So then let's plug in to this equation. Delta H of reaction is equal to delta H of the product minus delta H of the reactants. And when you do the calculation, product side is 0 because the formation enthalpy is 0 minus the product side, reactant side 34.3, it is negative 34.3 kilojoules per mole. When you calculate the reaction enthalpy, it is negative, meaning this is an exothermic reaction. Per mole of decomposition of silicon tetrahydride, it is producing 34.3 kilojoules of energy and transfer this one to the surroundings. Now, in order to tell if the reaction is favorable or not, we need to look at Gibbs free energy. Gibbs free energy is defined as delta H minus T delta S. Here, delta H value we found is negative 34.3. Let me look at the value. The negative 34.3 kilojoules per mole. Delta S, we just calculated 75 joules per mole K. This is a positive, which is 75 divided by 1000 kilojoules per mole K. Because delta H is kilojoules per mole, delta S is joules per mole. Always the case. Delta S is small value, delta H is a large value. So we need to divide by 1000 to make the formula, the unit equivalent to each other. Now let's plug in this one into the equation. Negative 34.3 minus 75 over 1000 times T. Remember that temperature is an absolute temperature, always a positive value. So then delta G is always negative. So I drew the graph at the bottom here. It is negative 34.3. This value is our y-intercept. This is y-intercept. And this is our slope. When you draw the graph, delta G versus temperature. Temperature is our x-axis and delta G is our y-axis. Then is y-intercept is negative 34.3 and slope is decreasing. As you see here, it is under the x-axis always, meaning that delta G is always negative. So when delta G is negative, this is a spontaneous reaction, and at all temperatures, delta G is negative, meaning that the reaction is spontaneous at all temperatures thermodynamically. The reaction is favorable, thermodynamically favorable at all temperatures. Now, we need to consider kinetics. So thermodynamics and kinetics are a different story. Like, make sure not to mix up between kinetics and thermodynamics. Let's draw the energy diagram. So here, x-axis is reaction progresses. So it means time. As time goes on, the reaction progresses from the reactant side to the product side. And y-axis, what is shown in the y-axis is potential energy, Gibbs free energy. Then, because this one is always delta G is negative, then reactant potential energy is higher than product potential energy. That's why I drew the reaction potential energy higher than the reaction potential energy, product potential energy. So delta G is always negative. And the reaction always, like mechanical potential energy, this chemical potential energy always moves to the direction to a low potential energy. So then when you only look at the product side, reactant side potential energy, the reaction must be going at all time, at all temperatures. But actually, it must overcome the activation energy hill. Okay, activation energy hill. So this is kinetics, related to kinetics. So the Arrhenius equation is telling us about the reaction rate. And in the Arrhenius equation, reaction rate is proportional to exponential. Here exp meaning exponential, negative activation energy over RT, which is 1 over exponential activation energy over RT. So when you interpret like this one, as activation energy increases, the reaction rate decreases because it is, exponential term is at the bottom of 1 over exponential, reciprocally proportional. What about temperature? As temperature goes up, then the activation over RT becomes low, and exponential term decreases, and 1 over exponential is increasing, so the reaction rate increases. So then our conclusion is like this way. So we need to overcome. We are looking at the kinetic term. When you're only considering thermodynamic term, it is favorable. But when you look at the kinetic term, the overcome this activation energy, make the reaction occur fast enough for our human, it requires high temperature. That's the meaning of this one. For example, when you look at between pure carbon, there are two forms of pure carbon. One is carbon diamond, second is carbon graphite. And carbon graphite is thermodynamically more lower in energy, potential energy, and favorable thermodynamically. But turning diamond into graphite doesn't occur. Why? Because it has high activation energy. So then practical sense, theoretically it is favorable, but practically speaking, it doesn't occur. Okay, now let's look at another case. A partial photoelectron spectrum of pure silicon is shown below. On the spectrum, draw the missing peak that corresponds to the electrons, the 3 pieces of shell. So relative number of electrons versus binding energy. The unit of binding energy is megajoules per mole. It is written as semi-logarithmic scale. So x-axis 0.1, 1, 10, 100, and 1000. As you see, it is 10 times when you from the right hand side to the left hand side. We call this one semi-logarithmic scale of graph. And relative number of electrons. So we need to look at the peak number of electrons. And here, electron configuration of silicon is again important. Let's look at the electron configuration. Let's revisit the electron configuration of silicon. Neon core 3s2, 3p2, which is 1s2, 2s2, 2p6, 3s2, and 3p2. Okay, so now let's think about the relative energy level. So potential energy is increasing from negative side to the bottom side to up. And remember that potential energy in this case, the electrons in the orbital and the nucleus, protons in the nucleus, it is always favorable between positive charge and negative charge. So it is negative. So then potential energy is all negative. Okay. Then when we take out electrons, binding energy meaning the amount of energy required to remove that electron from the atom. Then the distance between the ionization. Ionization meaning potential energy becoming 0. Okay. So as the energy level is higher, it is easier to take out electrons. And the 1s electron is lowest, and 2s, they are quantized. The energy level is quantized, and 1s and 2s, 2p has 3 orbitals, 2p subshell 3 orbitals, and 3s and 3p again has 3 orbitals. So it's taking smallest amount of energy to take out 3p orbitals, 3p electron, 3p subshell, and followed by more energy, 3s, more energy, 2p, more energy required to take out 2s electrons, and most amount of energy is required to take out 1s electron. That's why we see here. Okay, so then this one is 1s2, 2 electrons in 1s, and this one is 2s2, 2 electrons, and this one is 2p6. So relative number of electrons. So here, this one requires about 200 megajoules per mole energy to take out 1s2 electrons. This one is about 20 megajoules, and this one about 10 megajoules per mole, and this is 3s2. And then 3p2 should be close. So then number of electrons 2, and it should be close. As you see here, 2s and 2p is close, 3s2 and 3p2 is close. So this one should be the diagram. Remaining diagram. Smallest amount of energy is required to take out 3p electrons from the valence shell. I mean the highest energy level, 3p subshell. And H, using principles of atomic structure, explain why the first ionization energy of germanium is lower than that of silicon. We need to remind ourselves about the definition of ionization energy. Energy required to take away one electron from the chemical species, from the atom or an ion in gas state. Gas state is important. Silicon and germanium, it is solid state in room temperature. We need to evaporate it first, making it into gas. In gas state, we want to take out one electron, and it always requires energy. This is always endothermic process. That amount of energy called first ionization energy. Then let's look at about the periodic trend of the first ionization energy. First ionization energy is highest for fluorine on the non-metal side. Non-metal wants to gain electron to attain the stable electron configuration called the octet. So if we want to take away, non-metals want to gain electron, but we are going opposite of the tendency. Take out electrons, it requires high amount of energy. What about cesium and francium? It has one valence electron. It wants to donate this one valence electron to gain stable electron configuration in the previous subshell. So it is readily giving away. So small amount of energy only required to take out one electron from cesium and francium. So generally speaking, from the metal side, in the periodic table, left-hand side and bottom corner, to the right-hand side, upper-hand side, non-metal corner, first ionization energy increases. And in the same group, when you go up, the size is getting smaller. It takes more energy to take out electron. In the same period, when you move to the right-hand side, generally speaking, ionization energy increases because there is more protons in the nucleus. There is higher interaction, higher attraction to the valence electron. So based upon this periodic trend, we can explain it. Silicon, the most highest energy level is 3p subshell. Germanium is 4p subshell. So 4p subshell is further away from the nucleus than 3p subshell. So it takes a small amount of energy to take out electron from 4p subshell compared to 3p subshell. That's why the ionization energy of germanium is smaller than the ionization energy of silicon. So then periodic trend is very important. We need to understand relative, periodic trend of the ionization energy, electronegativity, metallic character, the radius and size of the particles. And this one is the last problem. A single photon with a wavelength of 4.00 times 10 to the negative 7 meters is absorbed by the silicon sample. Calculate the energy of the photon in joules. Let's think about the wavelength. Wavelength, we need to understand wavelength and energy. In the electromagnetic radiation, the light is called electromagnetic radiation in scientific terminology. 1 meter is equivalent to 10 to the 9th power of nanometers. So 4.00 times 10 to the negative 7 meters and multiply by the conversion factor, 1 meter is 10 to the 9 nanometers. It is becoming equal to 400 nanometers. And UV visible spectrometer is a very important equipment in almost every chemistry lab. So we need to understand, especially the visible light, its wavelength. We need to be familiar with the wavelength of visible light. It is in between 400 nanometers to 750 nanometers approximately, 400 to 750 nanometers. That's the window for visible wavelength, visible light. And the smallest wavelength, we have violet, blue, green color, and the longest wavelength starting from red and orange, yellow. So more like relatively warm color is located on the longer side, and the like relatively cold color, violet blue, located on the like shortest side of the wavelength in the visible light. So then 400 nanometers light is belong to the range of the violet color. Okay, let's think about this equation. Energy carried by a photon is determined by this equation by Einstein. Einstein formulated this equation: Planck constant h times the frequency of that light, the electromagnetic radiation nu. And more often than not, in chemistry, we are using wavelength more frequently than the frequency. Then the relationship between frequency and wavelength is c over lambda. C is the speed of light, and lambda is the wavelength. Okay, so now let's plug in. Energy carried by one photon is hc, h times the speed of light divided by lambda. Energy photon is 6.6 times 10 to the negative 34 joules times second, multiplied by the speed of light, 2.998 times 10 to the 8th meters per second, divided by 4.00 times 10 to the negative 7 meters. Let's take care of the units first. Here, second divided by second cancels out, meter divided by meter cancels out. The only remaining unit is now joules, energy. It's the only remaining unit. And this one has many large numbers, small numbers. 10 to the negative 34, this is extremely small number. 10 to the 8 is a large number. 10 to the negative 7 is also a small number. So students are struggling. You know, they may be able to set up this equation, but they are struggling to calculate it because it is a combination of very extremely small number and very large number. And how to deal with these numbers? It is better to separate the number and exponent. Okay, let's put them together, number by number and exponent by exponent. So 6.626 times 2.998 divided by 4, multiplied by 10 to the negative 34 times 10 to the 8th divided by 10 to the negative 7. And it is much easier to plug in these numbers into the calculator. Then I got 4.966 for the number portion. For the exponent portion, we can do calculation. And it is 10 to the negative 34 plus 8. So when the exponent is multiplied, the base is the same, then we can just simply add up the exponent portion. Divide by 10 to the negative 7. When it division, it is subtraction. So minus negative 7, which is positive 7. When you calculate it, it is 10 to the negative 19. So it's easier like not to use this like exponent portion altogether in the calculator. It's easier to make a mistake when you do that. When you separate like this one, it's better to calculate it. So it is 4.966 times 10 to the negative 19 joules. And because 4.00 has only 3 suffix, let's represent the number with 3 suffix. So from the next number, 6 is 5, 6, 7, and 9. We have to do round up. The final answer must be 4.97 times 10 to the negative 19 joules. I wanna go one step further. So this one is carried by a single photon, and single photon, let's look at the magnitude, 10 to the negative 19 joules. This cannot be, you know, measured, so small. Negative 19 joules, so small, 10 to the negative 19. So usually we need molar quantity. Okay, so then let's calculate the energy per mole of photons at this wavelength. So in order to do that, we need to multiply by the Avogadro's number. Avogadro's number is 6.022 times 10 to the 23rd per mole. When you do that, we multiply number by number, exponent by exponent. We found that it is 2.99 times 10 to the 5th power joules per mole. And this is a large number, and better to represent this number with kilojoules per mole, remembering that 1 kilojoule is 1,000 joules. So this one is 299 kilojoules per mole. Then this value can be measured. We have equipment that is sensitive enough to measure out this amount of energy. Okay, everyone. So in today's free response problem 2, it is asking a lot of concept about atomic orbital. Do you understand atomic orbital? Do you understand how to use the equipment to measure out and how to interpret the graph? In this problem, we saw two graphs. First one is, the mass spectrometry, mass spectrogram, and second one is ionization energy, binding energy, the graph. It's only asking you to interpret the two graphs. So interpretation of graph is important skill for a scientist and engineer, and this one is asking you. And then also a lot about electron diagram and the electron configurations and the relation, how to calculate the energy. Like using that equation, energy carried by photon is h nu, make a correlation with the ionization energy or something like that. Okay, thank you everyone for watching this video, and hope that it helps you to prepare for the upcoming AP chemistry exam.